Well, good morning, everyone. I'm Professor Brown. This is linear algebra, probably the coolest class in existence. I know I'm a little biased, but this is probably my favorite class to teach. This and Calc 1, just because of the abstraction and the stuff we do, it's very cool. As the students will always say at the end of the semester, you're going to answer questions where you didn't know there was actually a question. You didn't even know that was an area of mathematics, and yet you're going to be doing things that is beyond what you thought was even possible. And it's great. You don't need any technology to do what we're doing. Again, we're doing abstract spatial reasoning, multi-dimensional stuff. It's kind of wild. So I want to walk you through the Canvas. Is there anyone here who's new to Mesa this semester? Oh, good, because you guys are all returning students. Not everybody does the same stuff. I've had people tell me that they've had classes that they didn't even use Canvas. Canvas is a bulletin board. It's like Blackboard that we used for many years, except it's better. It's actually easier to use once you get the hang of it. It's a bulletin board where I put everything on there for you, but it's not a means of communication. No matter how many times I say it, I have people trying to email me through Canvas. Sometimes those emails get through. Most of the time I get a notification that somebody tried to email. And when I get that notification, I don't know who or for what, and there's no message, and I couldn't open it if my life depended on it. If you try to send me something through Canvas, it will always take it and treat it as a virus, and I won't even get that email. So if you want to email me, use email. Okay, I have an email. That's what that's for. And I'll talk about how to send me other stuff. So this is your Canvas homepage. Everything in the course is going to be located here under modules, just to make it easier on you. And the way it's divided, I have notes. Some of it's pre-written notes, and I'll be adding to this on a weekly basis, your syllabus, your schedule. The live lectures. Now, in Calc 3, many of you were in Calc 3. I had tons and tons of videos posted because I did a lot of the Calc 3 over the pandemic. Had to make a lot more videos. This class, I have videos from basically every lecture from last fall, but I want to do lectures and load them. So my goal is after every class, I should have that lecture up the same day. Okay, if all goes well, the same day. So if you were absent or you simply want to go over stuff again, particularly from Wednesday to Monday when you have time, it'll be nice because you'll have that ability. Back in the day, we didn't have that. As I was telling the class this morning, pre-2019, I've been here, it's hard to believe, this is my 37th year. And I know what you're thinking. He's not even that old. You're right. I was doing this before I was born. There were two teachers who taught online, and they were both stats classes. There was never going to be an online class taught at Mesa College through the math and science. That was never going to be a thing. It wasn't even going to be allowed. And then all of a sudden, everything's online. So we had to figure things out. I got all these extra notes, got all these videos. So you have access to things previous generations did not have. That's the one plus. So every day I'll be posting the live lecture, quizzes. I've already got the first couple on here. The exams, the exam keys, the practice test keys. Okay? So let's go to the schedule here for a moment. Now, one thing, if you're not familiar with this, when you want to open something, particularly if you want to print it, after you click on it, you got to go to the download here, and then look in the lower left corner, and then click on it again. They make you jump through a few hoops here. And I'll close that. Now you have the whole thing on the screen, and this is now easy to print from. It's hard to print from files, and it's hard to print if you don't go this far. Now this is a day-by-day lecture schedule. In the calculus classes, I actually put the topics that we're going to cover because in a calculus class, I might have 5 or 6 different textbooks being used in that class. In this class, we're only going to ever use one book because there's only one good linear algebra book. And this is the one I'm using. This is the 8th edition. How many have a copy of this, right? Does anybody have an earlier edition? A 7th edition would be okay. There's a few changes in the homeworks, but the order of the sections, it's almost identical. Anything earlier than the 7th, the changes are a little bit too much. So a 7th or an 8th, I was told there a rumor there's a 9th maybe coming out. If you go online and you want to buy this online, a 7th edition I've seen for under $30. This book brand new is like $250. You don't want to buy it brand new. This is the best linear algebra book produced. I have been actually using this author since the 80s, like first or second edition. Okay, there's a reason I like this author. I like the way they do things. There's a few things that I don't love, notationally wise. We can get past that. But for the most part, and I've actually had a lot of say in this book. I review a lot of textbooks. A lot of you don't know that. There's a lot of textbooks out there that the publishers will contact me, not to edit. No, edit means you proofread. Review means you tell them what you like, what you don't like, what you want changed. And whenever I tell them I want something changed, they actually do it. And I say this, not sort of half joking, but this is considered the #1 book in the whole world. So when they do the acknowledgments of the reviewers, what's the first name on there?
Oh, Michael Brown.
Mesa College, yeah.
Mesa College.
We're world famous here, by the way. Yeah, if you go to Mesa long enough and you have enough math books, you're going to see my name in a lot of them. I don't brag to say that. I say that because I want my foot in the door. I want to know what's going on. I want to know what they're presenting in the textbooks, because that's how I choose whether to use them or not, whether I like the way they do things. Sometimes I don't like the way they do things, so I don't use that book, even if I've reviewed it. This is a lecture-by-lecture schedule. What we're going to do, we will not deviate from this at all. I've taught this class so many times, I know how many minutes I need to spend on everything that we do. Some topics are much easier to grasp than others. Some are very difficult. The first few chapters, algebraically, are not very intense. Conceptually, they're not that difficult. Chapter 4 is going to be the most abstract stuff you've ever done in your life. You will long for the days of epsilon delta proofs. Right? Which are the worst things you ever did in calculus. What I always tell people, if you live through chapter 4, you'll be just fine. But it's a very abstract chapter, and we also spend a long time on it. So the way this class works, it's different from my calculus classes. My calculus classes, I generally do 1 quiz per lecture. Okay? This classes, I do 2 lectures per quiz. So the first 2 classes will be the first quiz, and notice the first quiz is due next Wednesday. That means the quizzes are always still due at least a week after the material has been presented. And so that will work all the way through. Here you see chapter 3. You see those 2 slashes. That's my way to indicate to you that's the end of the material. That's the first exam. And then you still have the quiz 4 coming up. So in the first 4 weeks, there'll be 8 lectures, 4 quizzes. We will have gone through all of them. We'll have keys, detailed keys. I will give out a practice test and a practice test key on the last day of material. And then the exam is 3 classes later to give you plenty of time to prepare, to practice. Again, most of you have been in my calculus classes. It's very similar. The #1 difference, though, it's not 1 quiz per class. It's 1 quiz per 2 classes. Partly is it's a shorter class. And a lot of the topics I have to do over the course of 2 days, and that just makes it easier sometimes to do it that way. At the bottom, this is the part that goes on your calendar on the fridge, all the important dates, when the exams are, drop deadlines, things like that. And again, we will not deviate from this schedule at all. We cover significantly more than any linear algebra class in the history of the world. The original textbook had 10 chapters. I used to cover all 10 back in the day. The 10th chapter, literally with technology, became more and more obsolete. It had a lot to do with estimations and things that you could get around technology, but with technology, the 10th chapter was it was applications. I stopped covering it many years ago. I cover the first 9 chapters, and you notice chapter 9 I cover right after chapter 2. 9 is an application chapter. It doesn't require any theory to understand, so doing it earlier actually makes sense rather than doing later. Chapter 7 is the reason you study linear algebra. Chapter 8 is the complex version of chapter 7. For most of you, you will probably have to take an upper division linear algebra because of your major. In an upper division linear algebra course, I'll use San Diego State, Math 524. The first day of 524, they might do a little bit of review, but on day 2, it's literally going to be the next day if you just finish this class. They're going to start with everything complex. So you want to have seen the complex here. Most people, when they teach this course, are hard-pressed just to get through the first 4 or 5 chapters, which is a shame, because chapter 7 is the reason the courses even exists. And that's the stuff you're going to use. How many here would say you are math or computer science? Okay, linear algebra is one of the most important courses. As a lower division course, maybe the most important. The only one that would rival it is discrete mathematics. All of your upper division math is based on these 2 courses for the most part. You don't do calculus anymore. other than upper level statistics, there's nothing else you're going to do that's calculus based. That sounds strange. Calculus is for engineering and physics. I love calculus. But it stops. Calc 3, you're done with calculus from that standpoint. Differential equations is an extension of Calc 2. It's not even Calc 3. It's lower than Calc 3 and from the calculus standpoint. You're just doing a lot of Calc 2 applications. If you're an engineer, that stuff is critical. For an engineer, I don't know how critical the linear algebra is. I know more from a math and computer science standpoint that it is one of the most, if not the most, foundational course. Okay, so that's why I get sad when someone says, oh, I took the 3-week intersession linear algebra. We actually had one for the last few years. They didn't get through chapter 4, by the way. And it was a checklist. Oh, I got that graduation requirement checked off. If you're required to take linear, it's probably because you actually need to know some linear. You don't want it checked off. You actually want the foundation, because I have not met very many people who needed lower division linear but not upper division. And you wouldn't have much of a chance in upper division if your lower division was substandard. Let's leave it like that. So you're in the right place. So we do some awesome stuff, some cool stuff. From a technology standpoint, you don't need any technology in this class, although I would like you to have at least a cheap calculator. And I don't say this jokingly. The vast majority of all errors you're going to make in this course are not going to be linear algebra errors. They're going to be arithmetic errors. And this is one of the, I find the irony funny, is the higher you get in math, really this is maybe the worst course. A calculator is a sign of weakness. That's literally the attitude people have in this class, in discrete, and DiffyQ. If I have to use a calculator, I'm not worthy of math. But if all of your errors are arithmetic errors, please have a calculator in front of you, right? You did fantastic mathematics, but have wrong answers because you're trying to do all of the stuff in your head. No, it's not, you don't need it. Now, do you need a graphic calculator? Not for linear algebra, no. There's actually never going to be a problem that we do that a calculator will really be of much assistance, because we're going to be doing stuff that's not really technology based. And I know people have taught this class entirely on a calculator. At the end of the course, their students couldn't actually do any form of linear algebra. You see, we're going to solve problems where the majority of our problems have infinitely many solutions. That's the standard problem. No technology can solve that problem. Technology can only solve problems when there's one solution. And that problem's boring. That problem's not even interesting to us. We're going to go over everything. Now, in terms of contact, my email address is on the syllabus. Okay, this class starts at 11. I can't imagine anybody's going to be hard-pressed to get here on time, but I have had people that literally, you know, they like to get up at the crack of noon, and that 11 o'clock class is a challenge. If you're running late, you're absent, quizzes due that day, do what every other group does. Get out your cell phone, take a picture of the quiz, email me the quiz. Don't convert it, just take a picture, email me the picture. The Fast Scanner app is the easiest one. The Cam Scanner is almost identical. How many have used either of those two apps? You know how easy they are and how fast they are. I mean, seconds. And if you're not sure, you go to YouTube. There's a 1-minute tutorial on how to use the Fast Scanner. It's actually that easy. I've even used it. That's how easy it is. I usually have to ask my kids for help when it comes to technology. They're so easy. But what that does, that's your insurance. You did fantastic work, but now you're not going to make it to class for some unknown reason. Get credit for the work you did. Okay, I can't accept late work, because if I accept late work, I have to accept all late work. And because I post a key, you know, that doesn't really work very well. So if a quiz is due at 11:10 next Wednesday, and you think there might even be a small issue of you getting here by then, send me the quiz and then come to class and hand me the hard copy when you get here. That's it. If you're absent, then hand me the hard copy when you get here. That's your insurance. You already turned it in. You did everything the right way. You'll get full credit for everything. It's pretty easy. Those who've been in my class, you probably got used to. How many used to email me everything just automatically? You didn't even think about it. Was it any work to do that? No. And it probably never mattered. But it's nice to know that, hey, you know what? That's the one day there was the accident on the freeway, and I never even made it to class because I couldn't get past wherever. Best excuse I ever had. It was within the last 10 years. I had a student email and said, I can't make it to class. There's a house in my driveway. And he sent me a picture. Somebody was actually physically moving their house. It was on top of a thing, and the people decided to park it in front of his house overnight. And when he went to leave in the morning, there was a house in his driveway. That's about the best excuse I think I've ever heard. He sent me the picture and everything, so everything worked out okay. I just wonder if you get a ticket for that, you know. You illegally parked your house or something. Okay. All right, so we'll get into some linear algebra right away. Now, the point, the term linear algebra is exactly what it means. We deal with linear equations, but linear equations with no limit to the number of variables involved. So let's start simple. Let's start with 2 dimensions. What would a linear equation in 2 dimensions look like? Well, it'd be a line. So if I'm solving problems, it's probably going to be more than just a line. So there's 3 possibilities in 2 dimensions. Let's start with this because this is our natural extension into 3 dimensions. Oh, are we recording? Okay.
Yeah.
We are, good. Almost forgot. Oh, I probably should use a fictitious name, huh?
I don't care.
Fred. Are we recording? Okay. The most common one, the one we start with remedial algebra in, I have 2 lines, and they have a nice, happy intersection. There are exactly 6 ways to solve this problem, believe it or not. In remedial algebra, the first way you do it is you do it by graphing because it's so easy to conceptualize and so easy to see, but it is extremely limited. Remember, I can only solve by graphing if my solution are integer values and relatively small integer values. You see, if I'm going to draw the graph and the solution is 10,365, 1,000,007. I probably don't have a piece of graph paper that big. So this is very limited, but it's the easiest to understand. So this is the one we start with in remedial algebra. I give you a nice happy line with a nice happy pair of integers. We know they don't have to be integers. We know they don't have to be small, but that's how we start. Then the second way we do it with 2 equations, we do the addition method. That's where you add the equations to eliminate a variable. Or the substitution, that's where we solve for a variable, substitute it in, and define the other. That's about the same level of difficulty, same amount of work. Then you take intermediate algebra and you learn how to solve it using a matrix, which is we're going to spend more time on that than anything else. That's a very powerful tool, particularly when there's more than 2 variables. I said, but there are other areas? Yes, you can use it by using an inverse. We're going to do that in a couple weeks. And you can also use what are called determinants. Some of you remember Cramer's rule. Okay, those are more advanced ways of solving. You typically reserve those higher levels when there are more variables. Because trying to do graphically when there's 3 variables doesn't work at all. I can't graph in 3 or 4 dimensions and you see the intersection. Using substitution or addition isn't really fruitful either. But with 2 variables, all those work. Now, the second one, I have 2 equations, and they produce the same line. And the third one, I have 2 equations, and they produce parallel lines. So these are the 3 possible outcomes if I gave you 2 equations in 2 variables. So this one we say is consistent with a unique solution. Okay? We say this is consistent and it is a dependent system. This one we say is inconsistent. Now, the first one is the one you like the most because it's happy, I can solve it. Heck, if my answer is ugly, I know there's techniques I can use. I can use my graphing calculator and I can find out the intersection. It's awesome, easy. This is really, really important in real life. And we'll do a few of those. This one here means there is no answer to the question. No matter how much work you do, you can't answer the question. So we will spend exactly no time on this one. The only one that really matters and is interesting and all of mathematics are based on is this one. Everyone's thinking it's the first one. No, it's this one. Infinitely many solutions, but I have to figure out a way to describe these solutions because in that description there is so much information that I can use. So a dependent system is the most interesting. Now, how do I know when it's dependent? Well, if I gave you 2 equations and I went to graph the lines and they turned out to be the same line, great. Now let's move to 3D. Okay? In 3D, what is a linear equation? It's not a trick question. In 2D, a linear equation is a line. What is it in 3D?
Plane.
It's a plane. Oh, okay, so you remember in count 3 perhaps, right? You have 2x plus 3y plus 4z equals 12. You know, but could it be x equal a number, y equal a number, or z equal a number? Sure. If I said z equal a constant, everyone understands this is the origin over here. That's the x-axis coming that way. That's the y-axis. That's the z-axis. If I said z equals a constant, that would be a horizontal plane that many units high above the xy plane. Okay, we know that because in 2 dimensions, if I said x equal a number or y equal a number, we know we get vertical or horizontal lines. Okay, so a linear equation in 3 variables is simply a plane in 3 space. Great. So think of the walls of this room. All right, I'm going to give you 2 equations. I'm going to give you the floor. I'm going to give you this wall. Oh, you want a 3rd equation? Okay, I'll give you the back wall also. Is there a common point of intersection? Yeah. So there's 3 equations, 3 variables. I got a unique solution. I'm going to give you the floor, I'm going to give you the wall, and I'm going to give you a 3rd plane coming in and cutting along this edge here. Think of that, call that the Rolodex example. Everybody know what a Rolodex is? All the index cards meeting at the center line. So I have these 2 planes and a 3rd, maybe a 4th, even a 5th plane, all intersecting along this line. Is it a consistent system? Yes, it is. Is it a unique solution? No, it is not. There are infinitely many, all the points on that line. Okay? I'm going to give you the floor, I'm going to give you this wall, and then I'm going to give you a 3rd wall that kind of makes it a triangular tunnel. 3 equations, 3 unknowns. Anybody want to tell me about that one? Floor, wall, diagonal wall.
Inconsistent?
Why is it inconsistent?
There's no point at which all 3 of them intersect.
Good. Oh, but there was no parallel. Parallel always yields inconsistent. Inconsistent almost never yields parallel. Parallel would be one example of an infinite number of possibilities. It's inconsistent because there was no point that was on all 3 planes. That's exactly the right answer. Now, what if I said floor, ceiling? That's kind of an oh duh, isn't it? I have 2 parallel planes. Obviously, that would be inconsistent. That's easy. But the problem is when I'm talking about planes, or we had more variables, is parallel obvious to you? Can you look at an equation when there's more than 2 variables and automatically sense parallel? It's a little more iffy, isn't it? I might have to think a little bit harder about that one. So the idea is, if there's no common point of intersection, it's inconsistent. We don't mess around that one because no conclusions can be drawn. There is nowhere to go. The problem's ending right at the very beginning. That's why we just don't spend time on it. We want to analyze the other guys. Well, we already know multiple ways of solving this one, and we know exactly how to express the solution. So the first thing I want to talk about is how do you express this solution? So let's start with something fairly simple here. So I have a system of equations. Let's say it's 2x minus 4y equals 12, and I've got y equals 1/2 x minus 3. All right, I want to solve this system of equations. And so what you did is, all right, let me draw them on my graph. So I'm going to I'll do this one first. So 1/2 x minus 3. All right, and now I'll graph this one. Well, let's see. I'm going to be lazy and just use the intercepts. So 6, 0, and 0, -3, and oh, same line, isn't it? I gave you 2 different representations of the same line. Exactly how many representations are there of this line? Infinitely many. Could I multiply both sides by 10? Could I add 4 to both sides? Yeah, there's an infinite number of things I could do that wouldn't change it, but I got one line. So in a baby algebra book, here's what they would say. This is what's called set builder notation. This is never the right answer to any question in this regard. We used this in count 3 when we were describing domains in 3 dimensions. But what they do, they'd say the solution is all the ordered pairs such that y equals 1/2 x minus 3. And that's a great answer, except I have no idea where on the xy plane that actually is. if I didn't start with the picture. So interesting, my youngest son, when he was taking, I think it was pre-calculus, he was solving problems and he got this type of situation. And he says, you know, Papa, I'm looking at the back of the book, and the back of the book says infinitely many solutions. But that makes it sound like the entire XY plane, therefore, is a solution. Now, am I right in that? When you're asking where on the XY plane, oh, there's infinitely many solutions. Doesn't that feel like they're saying everything's an answer? They're not saying everything's an answer, but they're not telling you where any of the answers actually are. I know, I want ordered pairs, people. I don't want equations of lines, I want ordered pairs. So this is a terrible answer. All I'm doing is restating the problem. I haven't actually told you anything. So what we're going to do is what's called parameterization. That's going to be the most common algebraic technique you're going to use. The only other time you really did any of this was at the end of Calc 2, when you dealt with parametric curves. A parameter is an external variable that you can use within the problem. So a lot of times you can let x or y be the parameter and then describe the other one. So for example, the way this one's looking, okay, I can describe this by saying, let x equal t. I'm going to pick a variable that's not being used. If that's true, then what would y be?
1/2 t minus 3.
1/2 t minus 3. Could I have just as easily said let y be t and then describe x? Yeah. In fact, that may have been a better choice because there's no fractions. So here's how we're going to answer this question. This question is going to be answered the set of all ordered pairs of the form t, comma, 1/2 t minus 3, such that t is an element of the real numbers. Now, this is the most complete, perfect answer, but I'm going to show you you can actually say less. I answered the question as an ordered pair, didn't I? I didn't answer it as an equation of a line. Now, pick a value for t. I don't know, how about if I pick t as 0? 0, -3. Isn't 0, -3 a point on this graph? Yeah, pick a different value for t. How about t is 12? So 12, comma 3. Is 12, comma 3 a point on this graph? Yes, it is. For every value of t you choose, you will get a different point on that graph, which means in this form, since t is any real number, there is an infinite number of t's, and all of them will produce a point on this line. Therefore, that's generating the entire line. But I answered the question in the same form that I answered the unique solution. I answered it as an ordered pair, but with the parameter. Could I have solved for y? Yes. And in fact, I'm a big fan of when you parameterize, avoid fractions if you can. You cannot always do that. But if you avoid fractions, it can make the algebra later on somewhat, you know, I don't want to say easy, but less mistakes. We make more mistakes because of the fractional manipulation probably than anything else. Now, if I don't put any restrictions on t, t is automatically a real number. Okay? Real numbers are the default. In certain contexts, if we were in a discrete math course, the default would probably be a rational number. Okay? If we were doing an upper division complex analysis course, the default would probably be it's a complex number, which allows for imaginaries and things like that. So to be really safe, I'm going to tell you that t is a real number. But if I don't say that, then it's automatic, that's what t is. We're going to do problems next that we're called traffic flow problems, where there might be a lot of solutions, but t will represent numbers of cars per hour, let's say. So now t can't be a real number, can it? T can't be negative. T would probably have to be a natural number, or at least a whole number, right? A non-negative integer. Oh, okay. So there are situations where t might not be a real number, and then I would simply state it in that form, that t is something else. But for most of the situations, t can be any real number. So there's a perfectly good parameterization. Wonderful. So parameterizing in general should be a fairly simple thing. Now, does it ever get complicated? Well, I said you really want to avoid fractions if you can. All right? Suppose we have something like this. 3x, let's go plus 5y equals 0. Now, this type of equation has a name. You would have heard this maybe in another course, but you may not have heard it, so we're going to introduce it here. Does anyone know what it is called when an equation is equal to 0? The form of this? Somebody say that for me.
Homogeneous.
Close.
Homogeneous.
Homogeneous. How many have heard the term homogeneous before? In what context did you hear it? Do you remember?
Milk.
No, that's different. That's a different. By the way, I'm glad you said that. If I take out the E, then it's homogeneous. If you were a homogeneous group of people, we would call you a fraternity or a sorority. Homogeneous means they're all the same. So that's what we do to milk. We mix it around so it's all the same, as opposed to milk that the cream is separated. That's why it's homogenized. Oh, homogeneous means they're all the same. It has nothing to do with mathematics. Homogeneous is not a term ever used in a mathematical context. Homogeneous has to do with it equaling 0. So if I give you several equations and they're all equal to 0, we call it a homogeneous system. So there's another word there, system. We'll use this word all the time, but a lot of folks, I always thought the front row people always go, oh, yeah, I have no idea what he's saying. I'm just going to nod so I don't look dumb. System is a very important term. System just means there's more than one. So that's an equation. This is a system of equations. That's all the word system means in this context. It's a system of equations because there's more than one. Homogeneous would be that the constant term is 0. Moving the 12 to the other side doesn't make it homogeneous. Homogeneous means the constant term is 0, right? So simply changing it is not quite the same thing. There is no constant term other than the 0. Now, when you have a homogeneous equation, the origin is always a solution. This is an extremely important fact that we will, completely abuse on a regular basis. A homogeneous equation always has the origin as a solution. I give an equation in 2 variables. I could give it in 10 variables. If I replace x and y both with 0, I know that 0, 0 is a solution. So the question is 0, 0 the only solution? Any homogeneous equation or homogeneous system equations has the origin. So when we say 0, 0 is a solution, there's another name for the origin. And I'm going to say the origin loosely, because the origin in 2 dimensions, the origin in 3 dimensions, the origin in 10 dimensions, just means they're all zeros. But dimension does matter. So this would be the origin in 2 dimensions. We have a name for the origin as a solution. It's called the trivial solution. That's a universal term. That's not a slang term. Whenever you hear the term the trivial solution, you literally are saying that the origin is a solution. Okay? Regardless of how many variables there are. So the trivial solution is always a solution to a homogeneous equation. The question is, are there other solutions? Okay? So are there other solutions? Well, how about if I picked x was 5 and y was -3? Would that work? Oh, now here's an interesting thing. When you solved quadratics, you could have 2 real solutions, 1 real repeated solution, or 2 complex solutions, which means no real solutions. So when you solved the quadratic, you had 0, 1, or 2 as an option. When you're solving a linear equation or a system of linear equations, an inconsistent system would produce a no solution. A unique solution would be exactly 1 solution. But there's a third option. With quadratics, it's 0, 1, or 2. With linear, it's 0, 1, or infinity. Yeah. Wow, that kind of jumped quickly. With a linear system, you can have the no solution, right, inconsistent. You can have the 1 solution, the lines crossed, or you have infinitely many solutions. That's your only other option. You can't have 2 solutions. So the moment I have a second solution, that automatically means what? Automatically infinite. And you can go all day, right? Like Captain America, he does this all day. Right? So if x was 10, then y would be -6. If x was 1,000, right, I can keep doing that. So I want to parameterize this. If I pick either x or y to be the t, then the other one's going to be a fraction. This is the easiest kind of parameterization there is, but I don't want to pick either one of them to be t, because I don't want fractions. Anybody got a clever idea? Because I want this to be the norm, that everybody would opt for the same thing here. How about if I said, let x equal, I don't know, 5t? then what would y be?
3t? Negative 3t.
Negative 3t. What if I said let y be 5t? Then x would have been negative 3t. Doesn't really matter which one I made negative. Why would I do that? Because now the solution is any ordered pair of this form here, and I have no fractions. So I said you want to avoid fractions if you can. Now, let me change the situation now. Any constant k. K is now any constant. Does this change me how I want to do this? Do I now want to pick either x or y to be t? No, actually, I want to do exactly the same thing. Now I'm going to have a fraction because of the k term. Unless k miraculously is a multiple of 3 or a multiple of 5. Oh, but it's these guys that I want to keep as integers. So let's suppose that I did the same thing. But now I'm doing it with this problem. So now I have 3 times 5t plus 5y equals k. So 5y equals k minus 15t. So y equals 1/5 k minus 3t. I'd throw this in there now. This will be fractional if k is not a multiple of 5. You all agree? But the parameterized terms, the t terms, I want those to have integer coefficients. In the long run, the most important part of the problem are the terms that have the parameters, not the terms that have the constants, strangely enough. Okay? So this is a suggested strategy for parameterization. Now, if either one of these had a coefficient of 1, if either one of them had a coefficient of 1, then you would pick the other one to be the t. So let's say hypothetically, make one more change. There. Now I want y to be t, not x. Because if x is t, then I have to multiply by 1/5 to get the y. I want y to be t. Because then x will be k minus 5t, no fractions. Okay? I usually make people recite it at this point in the course. In fact, this is very, very important. Okay? In the world of linear algebra, there's the 3 most important words that you can recite. Okay? I want you to look at me. Fractions are evil. Most of your errors, and I don't say this jokingly, I've taught this course for 1,000,000 years. Fractions are going to cause you more problem than anything else because you introduce fractions into a problem that didn't need fractions, and then we make arithmetic errors as a result. We get to the end of the problem, we can't figure out what went wrong. Our linear algebra skills are flawless, our execution, not so good. Yeah, so avoid introducing fractions if you can, because again, they will slow you down, plus I will make errors. Because I'm doing things by hand, and people just won't use calculators. I don't know why. Again, I really would like you to have a cheap calculator at your side so you don't have to do everything in your head. You know, sometimes you actually have to multiply numbers together. But for the most part, the numbers we work with will be small, so you really can do things in your head. But oftentimes, I want to check my solution at the end. Now, if an answer to a question involves fractions, there's nothing you can do to change that. But you can often avoid working with fractions throughout the problem. So first thing, we're going to go right into how to use a matrix. Now, I will assume everybody in here has some, no, I don't even want to say familiarity, some experience with a matrix. And right now that adds up to 0. We're going to start with a clean slate. Probably easier if you said, you know what, let me just forget everything I've ever learned and just start over, because the rules aren't that complicated. But a lot of times we get in trouble because we have bits and pieces of the truth, and so we'll do things that might not be legit. We'll do things that an operation that actually won't preserve a solution. And we don't even realize we're doing that. So, what is a matrix? Well, the formal definition of a matrix is it is a rectangular array of scalar valued functions. Ooh, that sounds complicated. I'm going to write it like this. Okay, the dot, dot, dot just means keep going. First of all, sort of the universal way of representing the terms in a matrix are with subscripts that refer to the row and column position. So it's always listed row by column. So, well, 1, 1, that's easy. Right? It's the first row, first column. This is the first row, second column, all the way to the first row, nth column entry, and so on. Everything's in a column or it's in a row. There's no randomness to this. So one of the things we want to identify is what are the dimensions of this matrix. The dimension of this matrix is always row by column. So it's m rows by n columns. Okay? If m and n are equal, which they will often be, probably more often than not we'll work with things where they're the same, then we say the matrix is squared. That makes perfect sense, doesn't it? So if it's 3 by 3 or 4 by 4, in fact, the most common matrix we're going to work with in this course is probably going to be a 3 by 3. Because if we can master everything necessary for a 3 by 3, we can do bigger. Bigger just takes longer. So there's a tendency that we'll do the smallest things that we can handle, to make big conclusions on. Right? That's the dimension. So if it's simply, it's a box that contains scalar valued functions. Now, the term scalar valued function, oh yeah, I know what that means. Do you know what a scalar valued function is? If you've been in my calculus classes, you should, because we use the term. We know what a scalar is. We know what a function is. So what's a scalar valued function? My numbers can be variables. My numbers could be sine x. That's not a problem. A scalar valued function has to, first of all, be a function of one variable, because that means when I evaluate at that number, I have a scalar. But if I had a function of two variables and you can only evaluate it at one value at a time, oh, I have a function of x and y, but if I evaluate it at an x value, I still have a function of y, don't I? That's not a scalar valued function. It's a function, but it's not a scalar valued function because there's no value that will ever produce a scalar. So in this course, we would never do a function of more than one variable in a matrix because you're never going to see that in any context. So I can have a matrix of scalars, I can have a matrix of functions of x, let's say, or functions of t, functions of a single variable. That way when I evaluate that variable at that number, boom, I have a scalar. There are going to be times when we actually do this with variables. Most of the time it's numbers. In a differential equations class, if you're using anything like this, it's always going to be variables. It's never going to be numbers. It's only going to be variables, but it'll be simple things. Okay? So the idea here is I want to use a matrix usually to represent a system of equations. That's the starting point. And I want to use a matrix to solve that system of equations. So if I thought of the algebra I perform on a system of equations, taking 3 times my first equation and adding it to my second equation to get rid of a variable, or switching my 4th and 5th equations to make it more convenient to me. There's algebra you would do on a system of equations. We want to know what algebra can we perform on a matrix that basically preserves the solution. Some legal stuff. If I do any operation that in fact could change the solution, then we'd say that that's not a valid operation. Okay, so there are exactly 3 matrix operations that are legal. These are called elementary row operations. And these are the only 3 that are legal. One of the problems that we sometimes run into is I'll do something that's not a legal row operation, but I got the right answer at the end, so that must validate it. I guarantee you, I'll take that same row operation and I'll show for the rest of your life, I can come up with problems where you will get the wrong answer. There's an infinite number of times that it won't work. Just because something worked once doesn't mean it's valid in general. It maybe you just got lucky. Okay? I have fun with this because I taught remedial algebra for years. And early on, I teach them how to manipulate negatives. And so what I'll do is give them a long sequence of negatives. It'd be like, -1 times -2 times the square of -1 times -1 times -2. I'll give them numbers that are 1s and 2s with lots of negatives. So the answer might be 4 or -4. But the idea was, when you're multiplying negatives, all you have to do is count the negatives. If you have an even number, it's positive. If you have an odd number, it's negative. And I would have people do this and get a right answer, and I'd mark it wrong. They say, why'd you mark it wrong? I got the right answer. I said, you made 4 errors. But I got the right answer. I said, well, if you'd only made 3 errors, you wouldn't have. In other words, I made 4 negative sign errors. So as long as you make an even number of negative sign errors, you're going to get the right answer. But that doesn't legitimize what you did. You got the right answer by sheer circumstance, right? If you only made 1 error, you'd have got the wrong answer. But as long as you made an even number, you're good. No, I said, just because you got a right answer doesn't justify the step if the step itself isn't valid. Because it means it might not ever work again. So the 3 things that we can do, and the idea is that we create a matrix that we call an equivalent matrix, not equal. For 2 matrices to be equal, they have to be absolutely identical in every way. I want a matrix that's equivalent, meaning I can get from one matrix to the other by doing one of these row operations. So it means I can also go backwards. So multiplying a row by 0, for example, can't be undone, can it? You never go backwards from zeros. So the first one is you can interchange 2 rows. So in terms of equations, that'd be like just saying I want to switch the order of my equations. I'm not going to change anything. The second one is you can multiply a row by a non-zero scalar. Technically, you can also do a variable as long as that variable isn't 0. So in the sense of an equation, if I took an equation and multiplied both sides of my equation by 10, I haven't changed anything. And then the third one, the one that's used the most often, so therefore probably abused the most often, I can add a multiple of one row to another, producing a new row. So I can take 3 times my first row and add it to my second row, creating a new second row, in other words. I'm not changing my first row, I'm just taking a multiple of my first row. These are the 3 legal row operations. You notice there's no such word as division, because there's no division operation defined. Matrix algebra, actually, as we're going to find, there's addition, there's scalar multiplication, there's really nothing else. We will define matrix multiplication, but there's a tendency people want to divide. They're like, there's no matrix division. I can't take the sign of a matrix. I can't, say, I want to just take the square root of a matrix. I want to integrate a matrix. No, there's just things that aren't there. I can add them, I can multiply them, and in row operations, these are the things I can do. So let's do a problem from beginning to end, just to see how this works. So we have, how about 2x minus 3y plus 4z t, whoops, sorry, not a matrix yet, I've got to make my equations first. Make sure it works. Okay, I want to solve this system of equations using a matrix. Now, we've never done this before, so we don't even know how to set up the problem. So I'm going to walk you through, because this is going to be an algebraic procedure that you're going to get really good at, you're going to get really fast at, you're going to get comfortable at. And what we're going to find is, for the most part, we're going to do things exactly the same way. People will hopefully all tend towards the most efficient route. Not just correct, but efficient. Anybody who remembers algebra, solving a system like this, and I combine equations, I'm across the board, and I still have 3 equations and 3 variables, don't I? They just look different than the ones I started. And I keep combining things and eliminating variables, and I never get anywhere. You guys remember doing stuff like that? Because trying to solve anything with 3 or more without using a matrix is not fast, it's not efficient, and probably you're going to end up doing a lot of circular reasoning. You're going to end up undoing things. So the first thing I'm going to define is what's called the coefficient matrix. This is generally the most important part of the problem. The coefficient matrix is the matrix of coefficients in exactly the order they appear. Never change things in writing this. You will change the actual problem. So 2, -3, 4, -1, 1, -3, 4, -2, 1. This is called the coefficient matrix. Everything's in a row or a column. There's no commas. Vectors have commas. Matrices don't have commas. Okay? The coefficient matrix actually will determine whether I have a unique solution or not. The numbers on the other side, if this system here, this is something that's going to be huge over time. If this system here has a unique solution, then for any set of numbers I choose, I'll get a different unique solution. And I will eventually get every solution in X, Y, Z space. If this one has a unique solution, then any question I can possibly ask, well, these are the only things I'm changing. Those do not determine whether you get an answer or not. This does. Okay, this is called the coefficient matrix. Now, what about those constants on the right? Now I'm going to add those to the problem. This is called the, oops, can't spell, the augmented coefficient matrix. To augment something means literally to add on. So when I put the constants at the end of the matrix, it's the augmented, and I want those constants there because now when I perform the matrix operations, I'll be able to solve the system easier. I can't solve the system without these numbers, okay? A lot of times, depending on what we're doing, and over the next couple of weeks, you're going to see there's many ways I can attack this problem. Having the coefficient matrix, I can use that to answer the question. I talked before saying there were other ways, using an inverse of a matrix, using determinants, Cramer's rule and stuff. That only uses the coefficient matrix when I do that stuff. Okay? So, now let's go over some terms. When you're looking at a matrix, starting in the upper left and moving this way, this is called the main diagonal. Starting in the upper left and moving diagonally. In fact, this would be the A11, this is the A22, the A33, and so on. Okay? A non-square matrix doesn't have a diagonal. A square matrix has a diagonal. So if I thought about, the square going from corner to corner of a square, but if I tried to do the same thing and I added more space, I wouldn't quite hit the corner. The coefficient matrix was a square matrix, therefore there's a diagonal. Okay? Now I'm augmenting it. You always start with the upper left position. Now, it doesn't matter what you're going to do in your strategy, you start with the upper left. This guy is called the pivot. This is the most important number. It's called the pivot. We really, really like pivots that are 1 or -1. We are really happy when our pivot is 1 or -1 because that removes a lot of the unnecessary work that we may have to perform. There is no such thing as you have to have a certain number for a pivot. We're going to do the third step. We're going to use that number to put zeros below it. So if this number is not a 1, it makes it difficult to take multiples of it. Does everybody see that? That's more work. Now, I can take, half of this and then take a -2. I can do things, but I'd really rather that be a 1 or a -1. It doesn't have to be. In the remedial algebra books and the pre-calculus books, they'll tell you the pivot has to be the number 1, period. Absolute, no questions asked. Okay, that is a lie from the pit of hell. That is not a requirement ever. It's a convenience. It is absolutely not a requirement. And in fact, most of the time, you don't even need the pivot to be 1 or -1. It's just convenient if it is. Now, how can I get a 1 or -1? I have a whole bunch of things. Now, if you were a computer A computer only has one way of producing a pivot of 1. Only one way. And that is to multiply that row by the reciprocal of that value. What's the problem with that? It means in the first step of the problem, you're going to introduce fractions. Fractions in a matrix are a virus. And I'm not joking. If I introduce fractions in the first step, then in the next step, every entry in the matrix will be a fraction, generally speaking. Is that wrong? No, but it's going to slow me down. Technology cannot strategize. Technology has to have a 1 in that first position and then use that. I could multiply row 1 by a half. I don't like that. I could take row 2 and I could add it to row 1. That would produce a 1. But there's one that's even easier. I said 1 or negative 1 is a perfect pivot. Anybody got a better idea? What do you think, Allison?
Like replace them, like you switch them?
Switch them. You know why that's my favorite? No arithmetic. I can't possibly mess that one up. Do a row switch. Okay? Now, what you generally want to do, certainly at the beginning, is always write down the steps you're doing. You don't have to do this, but it would be unwise to skip this. I'm switching row 1 and row 2. There. That's my indication that I'm switching them. I'm going to tell you why this is so necessary to do. Okay, I'm not touching row 3. But I'm switching these guys. Now, this new matrix is not equal to the original matrix because the numbers are different. It is equivalent to the original matrix because I could easily get back to the original by just doing another row switch. But now I have a pivot where all of the numbers below my pivot are multiples of the pivot. That's what you'd really like. Okay? What if my pivot was a 10? Well, what if the numbers below were all multiples of 10? Then 10's a perfect pivot, isn't it? It doesn't matter what the pivot is if the numbers below it are multiples. But the only way to guarantee they're always multiples is if your pivot is 1 or negative 1. Then everything below it's always going to be a multiple. Okay? So now, my next strategy, now that I have my pivot, is to put zeros in that column. It does not matter what's happening to the right of the first column. So I want to put a 0 in this position. I want to put a 0 in this position by now taking multiples of row 1 and adding it to the next row. So I'm going to take 2 times row 1 and add it to row 2, and that's going to become my new row 2. So I want to write it right in front of my new row 2. You're going to leave yourself, I call this a set of breadcrumbs, right? You guys all know about Hansel and Gretel, right? Although I learned a few years ago that they weren't just innocent children. They apparently hunted witches and things. I didn't know that. I always thought they were just little kids who got lost. But I guess there's a new spin on the story. But the idea of leaving a trail of breadcrumbs so you can find your way back. Plus, it's the only way you can catch an error. And there will be errors periodically. Okay? So I'm not touching row 1. I'm using it as my tool. It's my terminator. So when I take 2 row 1s and add it to row 2, that puts a 0. 2 of these added to this puts a negative 1. 2 of these added to here puts a negative 2. 2 of these, negative 24, added to this puts a negative 5. Now what the beauty is, if I use my pivot, I can do multiple steps. So I can do this again to row 3. What a lot of folks do is they'll do one operation and then do several matrices. That's correct. But when I'm using a pivot to put zeros, I can do all of those steps at one time. So I'm now going to take, how about 4 row 1s plus row 3. And that will become my new row 3. So 4 of these plus this, 4 of these plus this, 4 of these negative 12 plus this, 4 of these negative 48 plus this, that would be negative 35, I think. Okay? Now, we have created something here. You started in the upper left, you used that pivot to put zeros below. This is the strategy absolutely always. There is no other strategy you can start with. Now, here's a dangerous thing people will do. They'll say, well, I have a 1 here, why don't I use it to put zeros here? That's a great idea. I have a 1 here, I'll put zeros here, that's a great idea. Then when I go to row 1 and do it, I will undo all of the other work. if you start anywhere other than the upper left, then every step you did will be undone when you go to the upper left. You're going to undo every zero you put in. Therefore, it's kind of a waste of time. So you start in the upper left. So now I'm done. I have now created a mini matrix. This is what is called a minor. When you hear the term minor, literally it means a mini matrix. So think of, in a sense, mentally removing the first row and column, because you're done with those. Okay? Now, what's my upper left position? This guy. Is that a good pivot? It's a great pivot. If it wasn't, I'd make it a great pivot. And all I care about is putting a zero below it. I can do it above. I'm going to show you that one too. But right now, I just care about putting a zero below. So I'm going to take 2 row 2s and add it to row 3. I'm not touching row 1. I'm not touching row 2. 2 of these, see that 0 there? Can't change anything, it's still a 0. 2 of these puts a 0 here. 2 of these, that puts a negative 15. 2 of these, that makes that negative 45. Now, depending on what your overall strategy was, technically I'm done with the matrix. I can stop now with the matrix. And here's how you know. See that little stair step? That's one way of thinking about it. Other folks will say, take everything below the main diagonal, and I have all zeros. I have all zeros below the main diagonal. It's the same thing. That's my ultimate strategy. The moment I have all zeros below the main diagonal, I do not have to perform any more matrix steps. Now remember how we translated this. We translated this as this equation here. If I said, can you tell me the equations? You'd say, yeah, 2x minus 3y plus 4z equals 19. You can translate backwards. So look at my last matrix. What does the last row translate as in my last matrix? Does it translate as 0x plus 0y negative 15z equals negative 45? Wouldn't that be how it translates? Well, that would give me z equals 3. Okay, what does my second row translate as? Negative y minus 2z, oh, but I know what z is. I throw that over, that would give me y equals negative 1. And what does my first row translate as? Negative x plus y minus 3z equals negative 12. Negative 10, that gives me x equals positive 2, I think. If I didn't mess this up, we'll check in a moment. This is what is called backward substituting, what I just did. It's the most common way of solving the problem. I got to the end and I went backwards. I started with z, then y, then x. Okay? If I have made no errors, what is the answer to this problem? Remember, I'm saying, what is the simultaneous point of intersection of these? Is that the answer there? No. Z equal 3 can't be an answer. Z equal 3 is a plane. Or it's a single value. Either way, it's not a point. Oh, so I need x, y, z. I need to state it like this. If I have made no errors, this is my answer. And that's a huge if. If I have made no errors. Is it possible that we could have made an error somewhere along the line? Arithmetic. By the way, do you know what the most common error is? I'll give you a hint. It's because you guys are so overwhelmingly upbeat and positive. You may know what the most common error that you're going to perform and it's going to drive you crazy?
Drop a negative.
Dropping negatives. Yep. There's nothing more common than dropping negatives from one step to the next. And it completely changed every part of every answer. I just dropped a negative and nothing was the same as a result. And it will drive you crazy. The first few weeks, you are going to make mistakes that you've never made. Bad proofreading, You're going to look at the problem in the book. My favorite one is when you're looking at the problems, they're all really close together. This is the greatest error. I love this. I just kind of laugh. So you're looking at the problems in the text. So you write down one problem, and then you finish that problem by writing the first part of the very next problem because they were so close together. And you solve this problem perfectly. You look in the back of the book, and your answer's wrong, and you can't figure out why. Well, you did a perfect problem. You just didn't do the one, you took part of one problem and combined it with part of another problem because they're written really close together. So in other words, bad transcribing is probably the second most common error. It's not even bad math. Dropping negatives and writing the problem down incorrectly. So is it possible this answer is wrong? At the beginning of the course, it's highly probable. A month from now, it won't be. You will be so tired of redoing problems. I'm not kidding you. You will be so tired of redoing problems that your proofreading skills will be otherworldly in a month. Every class that's come before you, it's the same thing. You'll make mistakes all over the place now. You get tired of redoing things. You'll stop making those mistakes because you will create, you'll just be so much more focused. You'll create a way that you can check yourself really fast. I think that's the answer. How do I know?
Finding your originals.
Yeah. Now, the last equation, isn't this exactly the last equation that I used to substitute into? So I got news for you folks. It's going to satisfy this equation whether it's right or wrong. If I just said I don't have time, let me just make up values for z and y. Z is 13 and y is negative 27. Now I'm going to get an x. And it's going to check here because that's where I got it from. So where should you check it? Here and here. Check it in all of the other places. Now, I'll give you a hint. Do I really need to check it in all of them? No, it's either going to check in all of them or it's going to fail in all the rest of them. So I'll just check it in the first one. 4 plus 3 plus 12, that is 19. Right? Crowd goes wild, confetti everywhere, we got it right. First action logo, we didn't mess it up. You're going to make mistakes. You want to know that you can check it. Now, let's just suppose that we actually did make a mistake. And it will always be we made a mistake, not me. Okay, 'cause you guys are my eyes and ears. We made a mistake. Okay, I switched. Did I do this? Oh, I dropped the negative sign. The reason you write the trail of breadcrumbs is if your answer is not perfect and you didn't write down what you did, you have one recourse every time. You know what that is? Start all over and do everything from the beginning. And there is actually no exception to that rule. I deal with very smart people. That's not a joke. I teach the elite students at Mesa every semester. I'm very proud of that. But it's hard to convince people to write down their steps. But I can do everything in my head. Yes, and it means all your errors will also be in your head. And when you do everything in your head and there's an error, it is impossible to find it because you didn't write anything down. Which means you always have to do the entire problem from beginning to end. I'm really lazy. I hate redoing things. So I write things down. That way, if it didn't work, oh, here's where I made my mistake. I only have to fix it from that point on. I never have to start at the beginning. Now, my mistake may have been right at the beginning where I just wrote the problem down wrong. That's still going to happen. It's maddening. That kind of mistake still happens. Now, this is one avenue. Now, see, this is really, really interesting. That I drew it as little stairs. Okay? We're going to go back a few centuries, England. I have this gigantic Catholic kind of house, and I have all the dignitaries over and all the important people. We're all up here. Who's down on the bottom floor, by the way? Are the important people on the bottom floor? No, those are the riffraff, the peons, the other folks. All the hoity-toity, highfalutin people are on the top. Do you know the English word for stairs? It's not stairs. Echelon. Who are the people on the top? They are the people in the upper echelon. That's where the term comes from. It comes from English aristocracy. When you're on the higher floors, you are physically in the upper echelon. Do you know what this is called mathematically? Row echelon form. How many have heard that term before? And you go, that's what? Because it looks like stairs. Row, stairs, form. That's literally the translation. Row echelon form means my stair steps had zeros below the stairs. You can't be done if there aren't zeros below the stairs. or just below the main diagonal, same thing. Okay? This is row echelon form. Now, I'm going to go backwards a little bit because there are other ways I can solve this problem that are equally valid. Let me go, I'm going to go from here. Okay? Now, when I did this, and I did that, and I did that, and I got that, and I got that. Could I have put a 0 here? Could I have put a 0 above? Yes, we're going to do that. Okay, so we're going to take row 2 and we're going to add it to row 1, and that's going to be my new row 1. Now when I do that, I'm going to have negative 1, 0, negative 5, negative 17. Okay, I have a different strategy in mind now. Okay, my pivot. Okay, you notice I have only one value that's not 0 in this column. I have only one value. That's my new pivot. Here's what I'm going to do. I'm going to multiply this row by negative 1. I'm going to multiply this row by negative 1. You're going to like this. So 1, 0, 5, 17, 0, 1, 2, 5, and I'm going to multiply my last row by what?
1 over 15.
Perfect. And then I'm going to have 0, 0, 1, 3. There's my pivot. I'm going to put zeros above. So let's do negative 5 row 3s plus row 1. And let's do negative 2 row 3s plus row 2. 0, 0, 1, 3. So on top I'd have 0, 0, 0, negative 5 of these, that was a 17, so that's now a 2. Negative 2 of these, did I do that right? Negative 5 of these. Yeah, okay. So the negative 2 of these would be 0, 1, 0, negative 1. Now, see my coefficient matrix? It's 1s and 0s. But it's 1s on the main diagonal, 0s everywhere else. That's a very special form. I'm going to explain what that's called in a moment, the form that is. By the way, what was our final answer? Wasn't it 2, negative 1, 3? Can you read the final answer from this? Yes. This, when I first stopped, it was called row echelon form. I stopped the first time I could stop. But I've kind of gone to the ends of the earth here, haven't I? There's nothing else I could possibly do. This is called reduced row echelon form. And both ways are absolutely correct and equally valid and actually take about the same amount of work. I could have stopped earlier, but then I had to do all the algebra, remember? Or I just kept going. I know instructors, they'll just call this the RREF. But that's actually not a mathematical term. That's a visual description of what it is. The actual term, this is called, I'm a math guy. If you're going to say it, get it right. It's called Jordan canonical form. Jordan was a French guy, so I had a professor who refused to call him Jordan. He was just Jordan. You know, and he'd always say, we don't call him Michael Jordan, so, you know. It's called Jordan canonical form. Jordan canonical form is when you've gone to the ends of the earth. You can't do any more work, and therefore everything's a 0 or 1. Is it possible that the whole row could have been zeros? Yes. It's possible that I can't make it look exactly like this, but there's no more steps I could perform. So generally speaking, when you're solving a problem using a matrix, you go for row echelon form, which means zeros below the main diagonal, and now I can just solve it. Or I go for Jordan canonical form, which is the absolute most. Well, which one's better? They're both good, but if you have a dependent system, one that has to be parameterized, you always want to go this route. Because the parameterization, the algebra required, if you just are in row echelon form, the algebra is so much more work. And it is so much harder. So the moment you realize, oh, you know what, I'm going to have a whole row canceling out here, let me keep going and go for this. Then what will happen is you'll have something that is significantly easier to finish. Significantly easier. And that's going to be the most common problem. So they're both valid, and they both produce the same answer. Okay? So this is going to require practice. So today it's just, here's how you solve a problem using a matrix, not what do I use these for. Next day we're going to do two major applications. We already have applications. One of the things that I really love about this textbook is the last section in every chapter are applications of the math you just learned. Linear algebra is a very abstract subject, okay? But in every chapter you have absolute, really cool applications. You can say, oh, okay, that's where I can use this. We've all had classes where we're going, okay, I'm learning this math, but I have no idea how I would ever actually use this, right? This is how you would actually use this. So we have really cool applications just in the next day, the end of the chapter 1. Okay, so let me walk you through a couple small details. You're doing a problem, you're doing a matrix problem. Let's assume you've done everything right. Now, I said the most common problem that we're going to look at is a 3-variable, 3-equation problem. Here's why. The rules for 2 variables and 2 equations, some of the rules are different. There's things I can do when there's only 2 equations and 2 variables. There's things I can do that I cannot do in higher level problems. So conclusions that apply to 2-variable problems may not extend to highers. But the moment I have a 3rd variable, whether I have 3-variable or 3,000 variables, is always the same type of mathematics. And the conclusions and the strategies are the same. So rather than do a lot of 4 and 5 variable problems, we'll do a lot of 3 variable problems. Because if you can understand it for 3 variables, you can understand it for more. It's just that some of the things we're going to learn, like things like when we have calculated determinant, or finding the inverse of a matrix, or doing what are called elementary matrices, it's not the same if it's 2 by 2. It's completely different if it's 3 by 3, but 3 by 3 and 3,000 by 3,000 have all the same rules. So we tend to do 3 by 3 because it's the smallest problem that kind of covers everything. That's why. There's an old saying in mathematics that applies in many different areas. People say what's true for 3 is true for everything. But what's true for 2 is not necessarily true for everything. The moment you get that 3rd thing in there, it's probably true. It's kind of strange, but we'll see evidence of this over and over again. So we have a 3-variable problem. We're at the end of the problem, okay? And I'm just going to put, x1, x2, x3, x4, and I have 0, x5, x6, x7, 0, 0, x8. Okay, that's one problem. The x is just representing, it doesn't matter, they're just numbers, it can be anything. And then the 3rd case. So you've done all of your row operations that you want to do, and you got something like this. You've done everything, and your last row is going to be one of these 3. No matter what you did, if you choose to go back up and put zeros, that's fine. But in each case, I have row echelon form, don't I? Because in each case, I have zeros below the main diagonal in each case. You with me on that? Okay, let's start with the first one. How do I interpret the first one?
Z is 0. Z is equal to 0 in the solution.
So I have this many z's equals 0, so z equals 0. Everything's fine. For some reason, when we get a variable of zeros, we think we did something wrong. No, that's fine. What's the second one say?
Solution 0 equals.
This says 0 equals x8. How about if I write this? This is inconsistent. 0 can't equal a non-zero value. Those two that I just did are the two people tend to get confused the most often. The first one's totally okay, a variable equals 0. But the second one, it says 0 equals a number. Not good. What does the third one say? Technically, it says 0 equals 0. What does this mean? This means that I eliminated an entire row. A simpler way of thinking about this. I gave you 3 planes. I gave you plane, 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 unique point of intersection. I gave you plane, plane, diagonal plane. The intersection was still that line, wasn't it? The diagonal plane didn't contribute to the answer. It was still the floor and the wall. The diagonal plane was simply a linear combination of the other two. If I get a row with zeros, it means that this row or this equation was just a combination of the first two. It means I really didn't ever have 3 equations. I really only had 2 because one of them was completely eliminated by just combining them. So now I have 2 equations and 3 variables. This is a dependent system. It will have infinitely many solutions. It'll be all the points on that line. This is the most common problem we're going to look at in this class. This is the one we're never going to look at, and this is the one that confuses people because they think this one is this one. Do you see why that confusion is obvious? Because they don't look that different. So when you're doing a problem, the numbers to the left of the last column represent the coefficients of the variables. If they're all zeros, I better have a 0 in the last position. Okay, that's really the main thing. But if ever I have a 0 in the last position, nothing can be wrong. There's nothing wrong here. There's nothing wrong here. This is the evil one. Okay? Any question? This is day 1. This is not the hard stuff. It's very algebraic at first, and it's not complicated. Yeah.
For the row operations, you're doing like 2 additions at the same time. If you wanted to
If you're using the pivot, you can do 2 additions at the same time.
I was going to say if you want to do like row 2 added to row 3, and then or row 1 added to row 2, and row 2 added to row 1, you'd have to do that as separate.
No, yeah, you can't do that at the same time because then you'd get a matrix of zeros if you did that. So so that can you combine steps? What if we started the problem with a matrix of fractions? Yikes. My first row were all halves, my next row was all thirds, my next row was all 6. Is there anything wrong with multiplying each row by a scalar to make them integers? That'd be the same as multiplying both sides of an equation. That's legal. I could do that. So that's okay. But when you're using a pivot, you can use a pivot in every other row, but you can't simultaneously change the row you did the pivot on. Because if you could do that, then anything is possible. Any answer is possible. That's the only truly illegal step. But we're gonna figure this out as we go. Okay? Would you go ahead and stop that?